So today we're going to talk about the celestial sphere. What's the celestial sphere?
I don't think it's Greek origin, but like it's just where the constellations are in the sky compared to where the Earth is.
Okay.
Where on Earth it is, I guess. Not where the Earth is.
This is our celestial sphere model, right? Where does this idea come from? A celestial sphere. What does celestial mean? Sky, right? Something above sky, space, whatever. Celestial. It's not terrestrial, right? Terrestrial is Earth. Celestial is sky. Okay. So a celestial sphere is a sphere that surrounds the Earth, and what's embedded in the sphere?
Stars.
Yeah, stars, right? Why did the ancient people come up with this idea of a celestial sphere?
They thought they were actually points on a fixed object
Why?
because everything else moved, the planets moved, but they stayed the same.
Yes, the stars all move together, right? So it's all like their shift. The constellations don't change. We know they do, but we don't live millions of years. Our lifetime's way too short to see it. Okay, but all the constellations would move together and they would all spin together. Spin around what point? Yeah, the North Celestial Pole. And so it looks like a sphere just spinning around with all these dots on it. And then anything that moved was called a planet. In fact, the term planet means wanderer, something that moves around. And how many planets did they have?
4.
Huh? How many days are there in a week?
7 days.
What are days of the week named after? What is Saturday named after? Saturn's Day. What is Monday named after? What is Sunday named after? Hell, guess what? The sun and the moon, they consider planets too, because they move, right? Okay, now then it gets a little tricky. Because Tuesday, Wednesday, Thursday, and Friday are actually named after planets as well. I think Tuesday is Mars and the other ones. They work better actually in other languages than English. But they got translated to other languages, like they went to Latin, and then ours went to Old English, which has a Norse tendency, and then it got all kind of mixed up. So our thing, but they actually were the 7 planets represent the 7 days of the week. In fact, that's one of the reasons that the 7 became a week was because of 7 planets. Nobody knows for sure. This was long before written language, so it's the way it is. But all right, so anything that moved was a planet. Anything that didn't was part of the celestial sphere. Now back then, like the Egyptians, they didn't know what stars were. So the only thing they could think of that gave off light was like oil lamps. Because they would have oil lamps, that's how they would get light. And they imagine, oh, there's all these oil lamps that were on this sphere that would spin around. Okay. The reason we talk about it here is we know there's no stars on a sphere spinning around us. All right. But it's an easy way to think of and understand how and why we see the sky the way we see it. And you have to have an understanding of that to understand and say, oh, why can I see some constellations and some objects, but I can't see other ones? And when's the best time of year to see some and some other ones, and why do we see things the way we do? So we're going to talk about celestial sphere. All right. So the celestial sphere, this imaginary sphere, the circle's here. See, that was almost a perfect circle.
It was.
Not usually that lucky. All right, and inside this celestial sphere is the Earth. What do we use for coordinates on the Earth?
Cardinal directions. Or
North, south, east, and west. Where did they come from? Why is north that way?
Is it because of
Why did we make north that way?
rising, setting sun.
the celestial-
Okay, but that changes day to day, doesn't it? Where the sun rises changes.
This is because of the celestial equator and the
What's the celestial equator?
it's it's either longitude or latitude, I get it mixed up real bad. And it's where that is, it is where you stand, it's where the horizon is.
Did they know anything about celestial equator?
No,
Oh.
But they definitely knew about north, south, east, and west, didn't they?
Mhm.
So how do we define positions on the Earth?
Why or how?
1, 2, 1.
Yes. Both. How? The Earth is a sphere, right?
Yeah.
So if you have a ball, I should have brought my Earth globe. If you have a ball and you're trying to measure from one spot to another on a ball, or you measure like how many times it spins around, you have to like make a mark on it somewhere, right? And then you count how many marks go by. Where's our marks?
Longitude, latitude. Yes.
prime meridian,
Latitude, longitude,
You mean a starting point.
prime meridian, where'd that come from? But before you even do that, we had to have one very important one.
celestial pole.
The North Pole, yeah. We use the rotation axis of the Earth to define all the coordinates on the Earth. The good thing about the rotation axis of the Earth, that does not change. Now, the Earth shifts in its moment of inertia, those that have taken physics, does shift. As we have earthquakes and stuff, things change. But the rotation axis, there's so much angular momentum in the Earth spinning, it's not going to ever change. Well, that's not true. It is changing, but it changes so slowly that over our lifetime, over billions of years, the sun will die before the Earth stops rotating, okay? No fear there. All right, so we use the North Pole and the South Pole of the Earth as our reference point. We go halfway away from that, we get the equator, right? So
I'm thinking of the chocolate cancer every time I think of the equator.
A lot of us are too ingrained by other classes.
Yeah.
it's good. If you remember stuff from the other class, it's going to help you today. Okay? Which is good. This has been like a review for you, right? What is latitude?
No.
Degrees from the north celestial pole.
No.
How far from the equator?
How far from the
Equator.
equator? Hey, I like that one better. How far what?
North or south.
North or south, right? We can go either way. And what's the equator?
It's your right.
If you're defining things, you got to know what the words they use to define it is, right? What's an equator?
The part where no stars are circumpolar.
True, but that's not how they define it. How do you define what the equator is? No celestial sphere. Yeah, the midpoint between the North Pole and the South Pole. If you're going to cut the Earth in half, it's exactly between the North and South Pole. That's all I want. Okay? So we measure it from the equator, not from the North or South Pole. So it's kind of indirect. We measure from the equator, but we use the North and South Pole to define where the equator is. So really, we're defining it from the axis, but you don't measure it from there. Right? What's the latitude here?
0.
Are we on the equator?
Oh, you mean here?
Here, like right where you're standing in this room.
33 something.
Okay, for commerce,
Is it not 32?
33.
It's 32.
we're gonna go 33 degrees north. It's actually 33.2 or something like that. But we're gonna round it and just call it 33, okay? All right, well, used to be at the observatory, but I think it's all gone now. It used to be painted on the cement where that thing was. It had the actual latitude out to like 4 or 5 digits. It got it down to within like 10 feet. You can be that exact nowadays. We're gonna round it to 33 degrees north. What's that mean?
From the equator.
Yeah, we're 33 degrees from the equator to the pole, right? So what's the North Pole? 90 degrees, right? So we're about exactly a third of a way. Roughly. So we're up here, right? Here's our astronomer Herb hanging out so that angle there is 33 degrees. The latitude is the most important thing when you're figuring out what your sky is going to look like. Okay, because if you're at 33 degrees south, are you going to see the same stars? No. Which proves
So this is here.
the Earth is a sphere. Who said that? Who was the first guy to say that? He was a Greek, very famous one. It was Aristotle. Aristotle was the first one to say that, hey, as you travel north or south, you see different stars. The only way that can be is if you live on a spherical Earth. If the Earth was flat, it doesn't matter where you go, you're going to see the same stuff. All right. But there's still people that think the Earth is flat, just flat first people. I don't know how they get around that, but who cares, right? All right, so we got latitude, what's longitude? How far east or west of prime meridian? What's the prime meridian? Yeah. Greenwich, England. It's actually a suburb of London. Yes. Used to be its own place, but London got so big now it's just kind of a suburb. Travel there by train. I've been there several times. We have an observatory. Why? Why there? You can make the mark anywhere you want it. Why did they mark it there? Well, it was easier for the Brits. Yes, that's pretty much why. Because the British, when they decided to have an international standard, which was in the 1800s, the British had sent out all their ships in the 16th, 17th, and especially in the South Pacific, where they explored and got Australia and New Zealand and all the South Pacific islands. And they had them all corresponded to Greenwich, England. And so it was easier to use their system and then convert everybody else's. It's not like the French, of course, because they had their own system that went right through the center of Paris. And it's still there, which is kind of cool. You can go see that too. But yes, that's why that standard became. It's because it's like the British had the most charts based on that. Why is it based on Greenwich, England? How did the ship captains determine longitude? Does anybody know?
Didn't you say they just decided it because that's where they were doing the research? They just kind of.
Yeah, but why did ship captains? They decided because they had so many logbooks with it in there. But why did they use Greenwich, England as their reference? Because there was an observatory there. And what would the observatory do? Does anybody know? At noon each day, the Greenwich Observatory is actually up on a hill. It overlooks like the River Thames. And that's where all the ships were harbored before they would go off and sail all the way around the world. And they would have a ball in there and they would drop the ball. Exactly noon. And then the ship captains would set a clock to London time. And they would keep that clock at London time no matter where they went in the world. And then they would compare what time it was where they were by looking at the sun, local noon time, and compare that to London time, and they could figure out where they were in the world. The only way you can tell where you are in longitude is a difference in time. Otherwise, like if you're in Kyoto, Japan, which has a latitude of 33 degrees north, you're going to see exactly the same sky we do, exactly the same stars. They just see it 15 hours earlier. So all you can do is compare time. Well, then because the observatory was at Greenwich, everybody synchronized their clock to Greenwich. In fact, Greenwich is still the international time holder for the whole world. Everybody's clock is synchronized to Greenwich clock. In fact, they call it GMT, Greenwich Mean Time. They also call it Zulu time and astronomical time and universal time. Those are all the same times. They all are set to Greenwich time. All right. So that's why it ended up in England. Okay. Where are we? What's our longitude? In common. 95 what?
Degrees. West.
West. 95 degrees west. Because if you're leaving England, you go west to get here, 95 degrees. So we're about 1/4 of the way around the Earth, right? 90 degrees from England. If you went the other way, you go around the Earth and get here, but you're going 3/4 away. It's a lot longer way to get here. Good. All right. So back to our celestial sphere. So we have to have coordinates on our celestial sphere. It's still a big ball, right? So we're going to use the same coordinates. We're just going to blow them out into space, right? So right above the North Pole of the Earth is the North Celestial Pole. And down here is the south celestial pole. Okay, so far so good. So the equator is the celestial equator. Okay. So we have Earth coordinates, their latitude and longitude. We're going to do sky coordinates, which are
Right ascension and declination.
okay, which is which? Which corresponds to latitude?
Or latitude, right ascension.
Yeah, that's declination.
It's declination. You're right. It's declination. So declination is like latitude. Okay. So what am I putting up there? How far from what to what? North or of the celestial equator. Good. What's the declination of the North Celestial Pole?
Oh, no.
It's 90 degrees, right? What's the declination of the celestial equator?
0.
What's the declination of the South Celestial Pole?
Negative.
Negative 90. So it's positive, negative. Where latitude, you put a north or south behind it. For declination, it's positive, negative. Negative means south of the celestial equator, positive means north. Remember, we're very northern hemisphere biased.
It's kind of funny to me that they do put the east or west on one and negative and positive on the other.
Yeah. It's just the way it is, right?
Yeah.
What was the other one?
Right ascension.
What is right ascension?
That one has to be longitude, obviously, but it's also just because of the sun rising. Is that correct? Usually, We use it
Kind of
for
on the
that, at
right
least.
thing, but not quite. What is it? It's how far? No. It's actually only one of those. It's what? East.
It's east.
How far east of?
Primary.
There's no prime meridian in space.
Meridian.
No, well, no, there's a meridian, but it's a different thing.
How far is,
This- I'll let him go. I'll let him put.
no.
Around out of a mirror.
Yeah, well, we.
I think I know what he was talking about. It's the middle line for that's.
Yeah,
No?
meridian is right, but that's not what we're talking about. That's a different thing. We'll get to that, okay? We have to go back to the sun. This is where you were kind of right. If you remember the sun,
Oh, this-
Dang it.
yeah, it's slowly coming back here, right? The sun's orbit around the sky is called the
Solar.
ecliptic. Correct. What's the ecliptic?
At the sun.
Path of sun
Right here.
on the celestial sphere. Is it on the celestial equator?
No.
No, it doesn't. What's the angle? Is it always 23.5? You guys in Archeo should know better than this.
Yeah. We're trying.
Yes, it always.
Negative 22, 5 to 25.
5,000 years ago,
Oh.
when the Egyptians built the pyramids,
When it comes back.
it was closer to 24 degrees. It actually wavers back and forth, and we're at 23 and a half. Then it's going to waver back and forth. But it's on order of thousands of years, but it does change. I talked about that in archaeoastronomy, if you remember. For us in our lifetime, it doesn't change much, right? But if you're looking at ancient sites, it does make a difference. Okay, and so the path of the sun going around the sky, the ecliptic, we have 4 magic points on the ecliptic. We have the point where the ecliptic crosses the celestial equator there. And the path of the sun goes in this direction. Yeah, this is actually called the ascending node. What? I bet you haven't heard that one before, because I never talked about that in the other classes. A node is where they cross, right? Ascending means the sun's going from south to north. Back here, this would be the descending node. But they're more formally known as the equinoxes. We have vernal and autumnal. Which is which?
Spring.
Yeah, vernal means spring, is Latin for spring. Okay. So you say, oh, we have autumn, that makes sense. Well, vernal makes sense too. You're just doing it in a different language.
So the one in the front is the vernal. One in the back.
Correct. How do you know that?
Well, because if the sun's getting higher going that way, then that must be the summer direction.
You are totally right, right? Here we're going from the sun being low in the sky to high in the sky, right? Which happens at the vernal equinox, which is around what date?
March 22nd.
Yeah, give or take, right? We're going to say 22nd for all of them. It varies depending on the year. Why? Why is it sometimes the 22nd, sometimes the 21st? Leap year, because every 4 years we have to throw in another date. And there's actually more days in the last half of the year than in the front half of the year. Think, you go 6 months through that you have the equal number of days. That's actually not the case, right? Because February only has 28 days. And so in the last half of the year, from July through December, you actually have more days in the last half than you have in the front half. It's also because you have more 31 days. You have July, August, October, and December, all 31. More than in the front half. But it doesn't matter for us. It just means it's not equal. All right, the back one is, and when's that? Yeah, when's that? What's the date today?
September 13th. Next week. Next
Late next week, right? Okay. I think today is what, the 13th?
Yeah.
So the 20th, so it'd be like Wednesday next week. Give or take, right? It varies, but what's the magic point? What happens there? On the equinox?
It crosses the celestial equator.
It does. And what's that mean for us humans?
It's equal number of nights and days. I mean, equal
Not equal number, but the
hours.
equal numbers. There's the equal time in the day and in the night. That's where equinox comes from, right? That means equal night. And where's the sunrise?
Right.
Directly in the east. Only on those 2 days does it rise directly in the east and set directly in the west, which is the most dangerous time in commerce. Why? Because when you're driving on the road at the sunrise, you're looking straight into the sun, because our roads are all lined up east and west. Now, you guys probably weren't here, but about 6, 7 years ago, we had a professor that actually was killed over there in front of McDonald's. He went and got coffee from McDonald's. He was walking across the road. A lady turned out from that thing and ran right into him. And part of the reason was it was right at the equinox, and she turned, she couldn't see him because she was looking directly into the sun and just never saw him. It was kind of sad, but it was astronomically related.
I'm sure you waited a while to bring that up.
Yeah, I didn't say anything right away. What's this point? The summer what? Good. What does solstice mean?
Still. Sun's due.
Sun still, right? What day is that? Yeah, around the 22nd of June, right? Okay. And winter solstice, which is on December 22nd. Far so good. Okay. So since the sun makes this nice path around the sky, how long does it take the sun to go around? 365.24 something. Hey, see it. 1 year, right? It goes around 1 year. Now we know the sun doesn't go around the sky, we actually go around it. But to the ancient people, the sun moved around. That's why we have 360 degrees in a circle. The Egyptians knew that. Now they actually knew it was 365, but they made it 360. Why? Because they were obsessed with what number? 60. And 660 makes 360, which is why we have 60 seconds in a minute and all that stuff too, right? All right, so yeah, that's where we get 360 degrees from. It's close. Okay. Prime meridian, remember, we had to arbitrarily pick a spot on the Earth. We pick on the celestial sphere. Well, we already got this nice point right here. So the vernal equinox is where right ascension is measured from. So this is how far an object is east of the vernal equinox. Why only east? Why don't we go west?
The sun goes.
No, but you're on the right track.
So we measure azimuth in full 360.
Oh, that's a whole different thing. Hey,
Because it's the movement of all the stars
they all do what?
from east to west.
They move from east to west. Everything rises in the east. Why?
Because we are moving.
Because the Earth is spinning to west to east. So it's to make everything rise in the east, right? Okay. So yes, the way they used to measure right ascension when they first started calculating position is they used what they called a transit telescope. It was a telescope that would only face exactly south, but it could move up or down. They would go on a star and they'd say, okay, the star is here at exactly this time. And they would write down that time. And then they would wait, and the Earth would rotate, star would come up, and then there would time when it was there. And so they're measuring how far that star is east of the other one. And you measure east all the way around until it comes back around. And so right ascension is measured 0 to 24 hours. So it's not measured in degrees. Where declination, we already talked about, goes from 90 degrees to negative 90 degrees. But right ascension is measured in hours, minutes, and seconds, like time. Why? Just to make our life confusing. But it does. So the vernal equinox has a right ascension of 0 hours, right? What's its declination? 0 degrees. Okay. What is the declination of the summer solstice? Is it above the celestial equator? Yeah, so it's positive by how many degrees? 23.5. What's its right ascension? Are you sure? Yes, it's 6. I'm just making sure you knew. You were very like, you didn't sound confident. It's 1/4 of the way, right? This splits it exactly into 4 different points. So 1/4 of 24 is 6 hours. So this has a right ascension of 6 hours.
Is there a star or something at the, roughly at the point of the vernal equinox?
No. And it changes. Remember precession?
Yeah.
The whole sky shifts around. So at times there is, but right now there's nothing really there, no. Nothing bright. I mean, there's always faint stars. But what's the right ascension of the autumnal equinox? 12 hours. What's the declination? 0 degrees. It's back on the celestial equator, right? What's the declination down here? Negative 23.5 degrees. And the right ascension?
18 hours.
So what's the right ascension of the sun today? What's today? September 13th, right?
So it's somewhere
So give me an estimate.
11 to 12.
Like 20-ish hours.
11
No, we're over here, right? This is 22:12, right? So we're just before that. Yeah, we're probably like at 11:40 or something, right? Because we're only, and what, 10 days away from
Mhm.
something like
Less
that.
than-
How many hours of right ascension does the sun change each month?
Oh, it's point something. No, is it not point something?
I tend to see salary in full one.
How many months are there in a year?
So go like 12.
How many hours in the day? It's 2. This is not higher math. 24 divided by 12, right?
Oh.
Right, if it has to get back to where it was, 24 hours in 12 months, then it has to move 2 hours a month. So it changes by 2 hours a month. Okay? Roughly. You're like, oh, but that, we don't see that changing by 2 hours a month. Yeah, we don't. But if you measure it on the celestial sphere, it moves by 2 hours a month. How many degrees is that? I think somebody said that before. How many degrees in an hour?
15.
Right? The Earth rotates in how many hours?
24.
24 hours. And how many degrees does it take in one day? Right? If you reduce that, right? 24 actually goes into 360. You get 15 degrees per hour. So in 1 month, how far has the sun moved across the celestial sphere?
15.
2 degrees.
30 degrees. It moves 2 hours, right? 30 degrees. So if it moves 2 hours, it's moved 30 degrees. Or think of it this way. It has to go 360 degrees. It has to go all the way around once, right? Right?
Yeah.
And how many months are there?
12.
12. So what's 360 divided by 12?
30.
30, right? The same as 2 hours times 15. Just looking at me like, he's exhausted. This is not hard stuff, right? All right. Remember this, because this shows up a lot, right? When you're outside, remember if you hold your hand out like this, from the bottom of your fist to the top of your thumb, if you put your thumb on top, it's about 10 degrees. Okay. So if you go outside and you watch the sun and you're like, oh, how long is it till the sun sets? You just go like this and say, oh, the sun is about, oh, it's about 2 fists. That's about 20 degrees. So you're like, oh, it's going to set in a little bit over an hour, right? An hour and 15 minutes. So it gives you a rough idea of how long it'll take the sun to set, because you remember that it's about 15 degrees an hour. All right, it doesn't seem like much, but we're going to actually test that with our telescopes, and you're going to see when you turn off the tracking, our telescopes actually match the rotation of the Earth, so things stay in there. But if you turn it off, the stars actually move through there. You can watch them move across, and things just keep moving across, and they won't stay there. All right, so far so good. Everybody good with this? Okay, so everybody knows what right ascension declination is. We will use this a lot. Because we're going to be talking about the sky and what kind of things we can see and learn, right? And I say, okay, or I should ask this. What is the right ascension of objects that we could see tonight, right as the sun sets? Looking south. So south is this way. Remember in this building, right? North is that way. South is this way, right? Sunset, where's the sun? Yeah, in the west, right? It's going down right here. So how many degrees from south to where the sun sets? Yeah, exactly 90 degrees, right? If it's setting exactly west, which we're close to, right? Okay, so 90 degrees away. What's the right ascension of the sun today? You already told me. 11 hours. But 90 degrees is how many hours?
6 hours.
6 hours. What's 11 plus 6? 17. So things right as the sun sets, any object that has a right ascension of around 17 hours is going to be in perfect position to view. Anything the right ascension about 23 hours will just be coming up. Or essentially opposite the sun, 12 hours from where the sun is. Make sense? And then we rotate all night long. And then the sun comes up over here, right? And so the things that are close to the sun on the other side, you see coming up just before sunrise. So the sun during the night only really blocks a few stars around it. But it depends on what time of night, which stars you're going to see. All right. Which we'll talk more about next week when we talk about time. Here's my astronomer Herb. Herb the astronomer. Are we good? All right. North, south. Is east at the front or the back? You can't pick both. You can only pick one. It's in the back. East there. All right, so this is Herb going outside to the observatory. I didn't do a very picture. Herb should be right standing in the center. Okay. Right, if I'm facing north, my back is north. To my left hand is east, right? West. Okay, so here's Herb right here. I have it flipped around just to confuse you, but I want you to always draw pictures with north to the left, because then it's really easy for me to grade and see if everybody does it the same way. If you flip it around, then it gets confusing. Okay, so far so good. Can Herb see the north celestial pole?
Yes.
Can you see the North Star?
Yes.
If he's in Commerce, he can, right? Depends on where you are, but we're putting Herb in Commerce right now. Where's it at? Above. No, I'm asking where the North Celestial Pole is, so you can't measure from there. It's above the what? Yeah, we got to define a few things. This is called the horizon, which is the ground, right? If ground was an imaginary flat plane, that's where the term horizontal comes from, right? Okay. What's this imaginary line from north to south called? The meridian, which is what you talked about earlier. This is the meridian, and it goes through straight over Herb's head, which we call the zenith. Okay, all terms you need to know. Okay. Here's Herb, right? Anything you measure from the horizon up, we use the term altitude. It's how far an object is from the horizon. So what's the altitude of the zenith? 9 degrees, because it's straight up, right? What's the altitude of the nadir? Nadir is the opposite of zenith, it's actually straight down. It would be an altitude of -90. Nobody uses that term unless you do like crossword puzzles and it shows up every once in a while. But nobody uses it other than that. All right, so the altitude of the north celestial pole is 33 degrees above where on the horizon? The north point of the horizon. So from the north point of the horizon, if I go up 33 degrees, here's the north celestial pole. This equals your latitude in the northern hemisphere. Why do I have to qualify that and say only in the northern hemisphere? What happens if you're south of the equator?
You flip it. Or we
Oh,
connect.
but to the south of the two, still must.
Yeah, you look for the south celestial pole. Where is it? It's not above the north point of the horizon. It's above the south point. So yeah, this actually the whole thing. You can imagine this. Remember this continues to the south celestial pole over here. You just can't see it below the ground. But as you travel, this whole line just shifts together. It's still always going to be a line, but as this one comes up, that one goes down. So far, so good. Where's the celestial equator?
90 degrees.
Yeah, by definition, it's 90 degrees from the celestial equator to the north celestial pole. So if I go 90 degrees from here, I get the celestial equator. So that this makes a 90-degree angle. Good. Okay. And then, what is the altitude of the celestial equator? What is that green angle? What number is it? This is a half a circle, right? So the whole thing has to be 180, but I know this is 33 and this is 90, so I just have to subtract that, right? What's 180 minus 90? 90. What's 90 minus 33? 57 degrees. That is actually the most important number. But you're like, but our latitude tells us where we are. But this is technically what's called your co-latitude, 90 minus your latitude. Why is this important? Because if I have a star over here, and it's rising in the southeast, what direction is it going to go across the sky? To the celestial, so that it makes an angle of 7 degrees. When the sun rises, it makes an angle of 57. It never comes straight up, it goes at an angle of always and forever. If you stay at this latitude, it's never going to change. Right? Because the north pole isn't going to change, so everything will always go up at an angle of 57. Make sense? Okay. So if I have a star over here, it makes a big circle in the sky, right? But that angle is still, all of those are 57. They all go parallel. They're all like connected together. But if I get up here, these stars go around, but they never go below the horizon. Those are called what? Yeah, these are circumpolar stars. because they circle the pole, they never set. Give me a name of a constellation that's circumpolar. Part of it from here, if you went further north, where I grew up in Montana, yes, but not from here. Parts of it make it, parts of it don't. Give me another. The what? Little Dipper, Ursa Minor is, what about Cassiopeia, Draco, Cepheus, do you know any of those? Those are all circumpolar. Okay, good. What are the declinations of circumpolar stars? Sorry, that's in your way. What's the declination of circumpolar stars from Commerce? Where's declination measured from? Oh, celestial equator. So it's actually that angle. What's that angle? Yeah, how much is that? I can tell you randomly guessing at this point, aren't you? What's this angle from here to here? 33. So anything within 33 degrees of the north celestial pole is circumpolar, right? So that means this side is also. So what's the blue angle? Oh, hey, son of a gun, those match. Right? They're both 57. I told you 57 was really important. Anything, any star from Commerce, any star with a declination greater than or equal to 57 degrees will be circumpolar. Now that doesn't mean you'll see it the whole time because it's like trees and other stuff that gets in your way, right? But if you could ideally see a perfect horizon to the north, that would work. Notice those numbers are always going to be exactly the same. Meaning the altitude of the celestial equator is always going to be equal to the declination of stars that are circumpolar. Okay? Meaning if I change my declination, my latitude on the Earth, as this one gets smaller at the exact same amount. Okay, so far so good. I know this is getting complicated. A lot of lines in my diagram. But it all ties together. Down here, there's stars down here that make circles around the south celestial pole, right? We can't see these from here. I call them never visible stars. I never knew what the technical name was, so I made it up, but that's what we're calling them. It's never visible stars. What are the declination of never visible stars from Commerce?
Oh.
Where is declination measured from? Oh, which is up here. Hey, what's this angle? 57. Anything with a declination less than or equal to negative 57, you'll never see from here. Which are some places like the Southern Cross, Alpha and Beta Centauri, famous bright stars, large and small magnifying clouds. Need some of the best stuff. You can't see it, but travel. Okay, what's that angle? 33. Is this making sense? Maybe? It makes perfect sense when I do it. Right when I give you the homework and you're on there, you're like, what? All right, so far so good? Everybody's got this. Good. I'm running out of 4-6. What I've been talking to up to now is what's called the right ascension declination system. Best system for astronomers because it's tied to the celestial sphere, so that if I say right ascension declination, any astronomer in the world knows exactly where to look. Okay, they're just going to see it at different times in different places, but they know exactly where to look. It's like coordinates, it's like latitude and longitude. You tell somebody your latitude and longitude, they can find you anywhere on the earth. Right, that's the great thing nowadays with everybody having phones and stuff. Well, it can be good or it can be bad, right? They can find out exactly where you are if they track you down, which is good if you need to be rescued. Bad if you're running from the law or something. Okay, but there's another system. There's an altitude azimuth system. In this system, here's Herb again. North, south, east, west. We already talked about what altitude is. What's altitude? Yeah, how far an object is from the horizon, and above the horizon would be positive, or north of the horizon is positive. Or I should say not north, because it depends where you're here. Anything above the horizon is positive. If you're in the southern hemisphere, it's still positive if you go up. Negative is below the horizon. Yeah. And straight up is your zenith. Okay. Well, I could tell somebody where a star is if I told them how far up it is, which is just drawing a line down here. So that makes an angle. Saying this is your altitude, right? But I also have to be able to tell them where to look. So I can use the azimuth position, which is a position that says that north is at 0 degrees. East is at 90. South is 180 degrees. And west is 270 degrees. So essentially, I'm measuring this angle along the ground. So I start from north and I measure it, and they say, oh, it's at 148 degrees azimuth. I go until I hit 148 degrees. And the altitude of 42, I look up 42, hey, there it is. That's the altitude azimuth system. Okay. So what is the azimuth of southeast? The subcardinal point southeast. How about southeast?
Oh, southeast, that's 9. Yeah, 135.
Okay. 135, correct. Everybody get that? So southeast is exactly halfway between here, so I added 45 to 90. Or you can subtract 45 from 180, you're going to get the same answer, right? Okay, so that's how it's done. Now, the problem with the altitude azimuth system is as the sky rotates, stars not only change their altitude, they get higher, but they're changing their azimuth at the same time. Where with the right ascension declination system, that never changes. The right ascension declination are always the same. The whole coordinate system moves with you. And this is dependent on where you live, meaning it works fine for commerce, but if I told somebody in halfway around the world, oh, my altitude and azimuth is this, they wouldn't have a clue where to look because it's going to be totally different for them. Now we use it nowadays because it's easier to make big telescopes with an altitude azimuth system than a right ascension declination system. The good thing is we now have computers that can correct all those calculations every second. You didn't have to have somebody with a slide rule like you did in the past to figure everything out. So it makes life a lot easier. But I want you to know this system. Okay, not complicated. Let me check my notes and see what else I was supposed to cover that I haven't. Okay, let's just do an example that you're gonna have to do on your homework for next week.
I have a question.
Go ahead.
before we erase stuff. This might be stupid, but isn't like declination less than -57 something that would be like. Oh, never mind.
Like, what if it was -70?
So wouldn't it need to be like bounded on the other side, or are we just saying like
Well,
10 that are less than that?
I erased it, didn't I? What's the limit of declination? Goes -90, which is the south celestial pole. So yeah, I didn't write it, but really it would go -57 to -90. But yeah, it's kind of implied that -90 is as big as you can go. So. Yeah, you're right. And you have to think about less than negative means it's a bigger negative number.
Yeah.
It kind of seems backwards, but that's what I'm saying is -57, -60, all the way up to -90, which would be the south celestial pole. Yeah.
Is everything we do gonna be assumed it stops there, or are you gonna want us to do less than or equal to 90? Or do you?
Sorry.
Is it gonna be, like you said, it's assumed that it doesn't go above -57, or sorry, -90 on this?
Well, it's
one?
not assumed, it's by definition.
Oh, okay, okay.
By definition, declination can only go to -90.
Oh, I was just asking if you want us to write the less than.
Yeah, no, if you get something bigger than -90, you did something wrong.
Alright.
Okay, or bigger than +90, you're in trouble. Okay. Yep, okay. So let's say I know a star, like the star Vega. What's the declination of 38 degrees north? What is the maximum altitude it will get from Commerce, Texas?
Uh, 23.3? 0.3 something?
Nope.
Oh.
Let's draw a picture. All right, this is what I want you to do. And on your homework, I want to see pictures for every one of them. Astronomy is a very visual, spatial kind of thing. So I want you to draw pictures because that helps you to understand. So we're drawing the Herb diagram, but we're just going to do it 2D, just north and south. We're not going to worry about east and west because maximum height always occurs when you're on the meridian, right? Everything rises, gets higher, hits the maximum on the meridian, and then it gets lower again. Yeah, why'd you put a north there? I'm talking to myself. No, I should have just 38, you're right. Correct me when you find things I do. I make as many mistakes as you do. The way it is, I just keep correcting. Part of life. Now where are you? Where do we live? Commerce. So you have to know where you are. So we're doing it from Commerce. And what's the latitude of Commerce? And then we need a north, right? Okay, now what? Draw what? Draw the north celestial pole. Where?
32 degrees above the ground.
Yeah. We need to do this. We need to always put, first step, put the north celestial pole. And how do you know where to put it? You always put it so this angle is equal to your latitude in the northern hemisphere. If you do south celestial pole, which we're going to do in this class just to mess with you, you do it on this side. It's like a mirror image. Okay. First step, so you get the north celestial pole. Second step. Yeah, second step, you put the celestial equator where? 90 degrees away. Step 2. Step 3. Determine the altitude of the celestial equator. So you find this, and we always do this by 180 minus 90 plus 33, right? We're going to get rid of all that. And we'll leave that. Okay, it's always going to be 90 plus your latitude. Or just 57.
Yes.
Right, okay. It's the same thing we did before. We're just doing it again. This is 57. Where's Vega? How do you know it's north? Positive. Remember, declination is always measured from here. That's why we have to get this on our diagram. So once we know that, then we know where to put it. So I'm going to go 38 degrees. There's Vega. Yeah. That didn't answer my question. What was the question? Yeah, what is the altitude?
57 plus 38, so 95 degrees.
Yeah, but look. If I do 57 plus 38, what do I get? But altitude can't be bigger than 90. Oh, no, we broke it. If you're bigger than 90, it means you have to measure from the other side. All right, essentially, this is it. Instead of going straight up, you went back like this. So instead, you should have turned around and measured from this side because you can't go bigger than 90. So what do? You just take 180 minus that. Get the answer. Okay, so if you get it bigger than 90, take 180 minus that. If you had a class from me before, you probably saw a lot of this. If you haven't, this might be brand new. Also explained in more detail. Some people say in more detail than you want to know. The first chapter of this book is all about the celestial sphere. All right, which is what we're covering this week. Good with that? And all right, yeah, I think that's pretty good. Any questions about this? Okay, good. Put that up there. What we're going to do, we're not going out to the observatory because it's cloudy. It's partly cloudy, but it's more cloudy than we can deal with. And it's still not getting dark until late. So hopefully next week we'll go out and we'll put the telescope up. What phase is the moon?
Oh, it works for quarters.
You're close, but the first part's wrong. Waxing. What's waxing mean?
Slowly growing.
Getting bigger, right? Waxing is getting bigger, wingers getting smaller. So what phase is it right now? It's a waxing crescent, but it's the waxing crescent is getting close to what?
Yes.
Getting close to yes.
Oh, I was saying yes to these.
Getting close to first quarter, right? So next week, what phase will it be? Next Monday? Let's say it's first quarter tonight. It's not, but if it's first quarter tonight, what would it be next week? Full moon. Somebody remembers the moon phases, right? The moon takes a month to go around, 29 and a half days, right? So it goes through each of its 4 phases in about a week. So if we're close to first quarter, it's going to be close to full moon next week. Okay. Now we'll still go out there if it's clear. I told you sometimes we won't go out if it's full moon. But since we're just learning how to set it up, we can still see bright stars and stuff. We'll be fine. Because if you try to look for fake things, you can't see them with the full moon. It lights up the whole sky. So astronomers hate them. It wastes about 1 week every month that we can't actually do research because the moon's in the way. But so today we're going to do an activity. We're going to use the celestial spheres. So each person go grab a celestial sphere. Actually, what I need is a tall person. You're lefty.
6 foot.
Well, you're that's taller than I am. Is anybody taller than 6 foot? Can you reach him? All right, so he's going to hand each of you one of these. Bring it back to your. So run over there and grab one. I think we had enough one for everybody. What's it? Believe me, I'm not tall, so I don't win any height contests. You know what? You like us watching and freaking. I'll be right back. I'm gonna run and copy this off.
Yeah. I was gonna say that it was so bright. Must be like the sun.
My calendar had 6:30. I was here twice.
Mine doesn't have a moon. Oh, wait, never mind. Yeah, where are you?
I can, so I don't have it. Yeah.
Titan. Broke it. Good job, Brad, you broke it. Hey, go up here and go like this. Yeah. You gotta type. And since you turn it this way, that can probably reverse thread. What's up the other way?
Was not working this Friday.
The moon doesn't move.
Seriously?
I don't know.
Your moon- your moon just throw this-
Fail or something?
There's some putty online.
I don't know what you're talking about, but the moon does not move.
Cause I got a
Look,
text
there's
from
putty.
Dr. Davis, like a group chat. He was like, who wants hours? Probably because you are working Friday, you weren't at it, just because you don't need that help.
Yeah.
It's already working.
Just on the spinning.
Wednesday, and then hours Saturday.
We need to replace the staff position.
Yeah. Okay, so you were at.
It seems that they're using that.
Okay, let's just pretend that. No.
Oh, yeah, look at it. That's what I'm saying.
I'll be out.
Yeah, that's.
Okay, so we have.
You gotta go manually.
I'm pretty sure.
It's acrylic. Like at all. You gotta move.
Power over
Those
the
are-
earth and moon.
You have to stop the moon.
That the moon doesn't move. Are we gonna need to move the moon? Because my moon doesn't move.
You don't have a moon.
Oh, is that the sun?
That's the sun.